Welcome back to this tutorial series on implementing numerical methods in Python, and in today's video we're going to be finishing up going over the chi-square distribution. In the previous video we went over the p-chi-squared function and how to derive it and how to calculate it, and in today's video we'll be going over the q-chi-squared function where you give it a probability and a degrees of freedom v. It is known as the cumulative distribution function, the CDF. So given a probability value, calculate at which quantile value does the area underneath the function equals the probability. It is known as the inverse of the PDF. So for example, in our p-chi-squared, you would give it a quantile and a degrees of freedom. It would return an alpha value, a probability value between 0 and 1. The q-chi-squared, you give it a probability value between 0 and 1, the degrees of freedom, and then it returns the quantile value. So here we have q-chi-squared of 0.95 with 4 degrees of freedom, and it returns 9.48. And now I'm going to show you guys exactly how the CDF is derived. Well, not necessarily derived, but what it equals. So here we have our CDF of our chi-square distribution. So what this simply does is it gives us the probability on the x-axis, and it gives us the quantile function on the y-axis. So in the previous video, when we plotted out the PDF, it was the quantile on the x-axis, and then it was the alpha value on the, the probability value on the y-axis. But now it is the inverse of that. And so what it is it's the 1 over the gamma function. This is the complete gamma function, as we've gone over before. And then here we have another gamma function, except this time it goes from 0 to z instead of 0 to infinity. This is known as an incomplete gamma function, most notably the lower half of an incomplete gamma function. So it is 1 over the gamma function times the incomplete gamma function. And so what we do here is this returns a probability value. So in order to solve at which z value, or our quantile, does a probability occur, we need to make it a root finding problem. So here I have p representing our probability. I just shift it over. So now we have a root finding problem, and we need to see wherever this occurs. So the root is at 4.744, and what this is set up to right now, our beta is 2, because beta is always 2 in a chi-square distribution. Our degrees of freedom is 4. So in the previous video, if we were to give a degrees of freedom of 4 and a quantile value of 9.48, our probability would be 0.95. However, this time we have the probability we want to calculate at which quantile function this occurs at. So we know the probability, and so the root is at 4.744, and this does not seem to be 9.48. However, hidden underneath this is if you times 4.744 by 2, you get 9.48. So without going into much of the mathematics behind this, I'm just simply going to throw this out there, and we're going to use it. So what you do here is you take your probability value. So let's say I wanted to find the 50 percentile. You simply just take your function and then you turn it into a root problem, and then you find your root, and then you times that by 2, and that is your given quantile. So now let's actually implement this in Python. So we'll say definite function, def q-chi-squared, our probability, and degrees of freedom. First, we need to check to see if our probability is between 0 and 1. If it is, then we're going to say print error probability must be between 0 and 1. Return none. And then what we need to do is calculate our alpha for a chi-squared distribution, which is always degrees of freedom divided by 2. And then what we can do here, if I was to bring this back, this value right here is a constant. So what we need to do is we can calculate this as a constant and pull it out. So the only problem in our root, the only thing in our root finding problem that's going to be an issue is that we need to iterate over this integral. So we actually need to have a root finding problem specialized for our integral. So we're going to define our own root finding method. So instead of using our previously defined bisection method, we're going to make our own version of the bisection method. Now, instead of using Newton's method, the problem with Newton's method is simply that it would be extremely hard to find the derivative of all these, and second off, it requires a close enough initial value. And so instead of just using the bisection method for 20 iterations and then plugging it in for Newton's method for 1 or 2, we can just use our bisection method for 20 iterations and find it to the tolerance of like 1e to the negative 4, because that's all we need it for. So we need to calculate our constant, and it is given by 1 divided by the gamma of our alpha. So that is this constant right here, and we're going to make our tolerance is equal to 1e to the negative 6. And then what we need to do is import Euler's number again. Give some room. Have our maximum iterations for our specified bisection method as 300. And now what we need to do is make our function for this. So we're going to use our calculator and our parser. Just like here, we're going to make our function, make our scanner, and make our parser. So we're going to say function is equal to x raised to the a minus 1 times e raised to the negative x. And what we also need to do is times our constant by this value. So we have our constant times this. So that's our function. Let's get our tokens. And make our parser. And now let's actually add our variables. So we're going to add our variable c. We're going to pass in our constant. So every time we call our function and we see c, we're going to use the constant value. We're going to add our a as our alpha. And we're going to add our e for Euler's number. Now we're going to be going over our root finding. So as I stated before, we're not going to use our predefined bisection method that we made in earlier episodes, simply because that dealt with a simple function. Here, our root finding problem is going over an integral. So we need to find the root, exactly at what z value does this equal 0. So we need to loop over the integral. So we're going to say our iteration is equal to 0, and we need our interval from a to b. And so now we need an interval, a and b. And what we're going to do is, because the chi-square distribution only assumes positive values, we cannot choose a negative value here. So what I'm going to do is I'm going to choose a value extremely close to 0, probably 0. A is equal to 0.000001. And now we need our b value. Well, how far would this actually go? So here we have a root. However, if we change our degrees of freedom, which here is v, our root is going to change as well. So it depends on how far we want to go as our ending location, depends on our degrees of freedom. However, degrees of freedom in a chi-squared distribution represents the number of variables. So most likely, let's say if we had a data set with 50 variables, our maximum x value is going to be 24.66. And so simply what we're going to do is we're going to limit this. If I was to keep on going to 60, for example, so the maximum value probably is going to be at 50 to assume all possible values of our degrees of freedom. So we're going to stop at 50. So our max possible x value is going to be 50, which is our b. So this is going to allow us to have an extremely large number of degrees of freedom. Or actually, let's make this 40. So now we're going to make our while loop to loop over in our bisection method. And what we do here is we take the medium value, so we take our a plus b, divide it by 2. We take the middle value, and now what we need to do is calculate our f of a, which is given by adaptive composite substance calculator. So we're going to integrate using our parser our tokens from 0 to a using our tolerance. And then our f of m is equal to our adaptive composite substance as well of our tokens, this time from 0 to m of our tolerance. And one thing here, if I was to go back to our original equation, it is p minus this value. So we need to have our probability minus this. And the reason why we're integrating is because we're trying to find out what z value does this equal 0. Because this right here is a constant, and the only thing that's, and this right here is also a constant, so the only thing that's changing is our z value. And so what we need to do is make a bisection method over this integral and find out at what z value does this equal 0. So we're going to go from 0 to a, 0 to m, and just like before, we're going to say update our iterations. We're going to say if f of a times f of m is less than 0, then we make our b equal to m. If f of a times f of m is bigger than 0, we make our a equal to m. So let me go back and change our degrees of freedom to something reasonable, such as 4. And so let's say here we chose 0.0001 and 40. The midpoint would probably be about 20. In this case, we'd probably take our value of a, which is positive, our m value, which is negative, so we get a negative value. So then what we do is we assign b equal to m, so then we assign b equal to 20, and then we take the midpoint of that, which is 10, and we take the midpoint, take the midpoint, take the midpoint until we have a positive value. So else, this either occurs on f of a times f of m equals 0. Therefore, f of a or f of m equals 0. We're going to break, and we want this to happen. However, this does not usually happen if we find the root explicitly, so we're going to make a tolerance level. So b minus a is less than tolerance, because from both sides, b is going to approach our root, and a is also going to approach our root. So if these two values subtracted from each other or is less than our tolerance, then we break. If our iter equals max iter, print maximum iterations reached. Return none. And then what we're going to do is we're going to say print iterations needed, string of iter, and normally we would return m. But like I said before, our root is not necessarily the x quantile. It is 2 times our root. So we would take 2 times our root value, and that is the given quantile. So now let's actually run this. Give a short example. So print qchisq of 0.95, 4 degrees of freedom. This should return 9.48. So here we go, returns 9.48. It took 26 iterations of our bisection method. So hopefully you guys have learned a lot from this. In these past 2 episodes, we've went over the chi-square distribution, how to calculate it numerically, how to numerically calculate the cumulative distribution function and the probability distribution function. And both of these functions are found in R as well, so we've also replicated these functions in R. And so hopefully you guys stay tuned for the upcoming videos where we go over the normal distribution. So stay tuned.